All right, everybody, we're in session, and I just want to get my screen shared quickly, my iPad. Okay. So I can get this going here. All right, this works. So let's just pull this out of here. Okay, I want to get back to our class, which will be ENEE350 right here. Right there. Okay. So last week we, I guess, did a couple of examples in VESP 2.0. We looked at, for example, how to search for an element. And then, of course, this was all based on our VESP 2.0 instruction repertoire, which included these two nice instructions that, useful instructions, which are basically MXF and MXT, in addition to some other instructions like increment and decrement. And so, yeah. I'm just checking to see exactly. So this was the original program, which we had, if you remember. And we were just simply finding the sum of a bunch of numbers in a particular array that we stored in the memory of VESP. And then the next example we did in class, I didn't get to run it. And I suggested that I guess you guys maybe try this and see if it works or not, was to search for an element in an array. And again, our array was sort of like kept in that same set of locations where we put, I guess, numbers from 1 up to 10, and we were just looking for, I think, key being 5 here. I could see that. And so we did that. Now, the last example I mentioned, which I didn't get to do or complete, was this sorting problem. And, I was, I guess, using some sort of a selection sort mechanism here. So maybe I can just show you a little bit more detail. I may not end up writing the entire code because it may be a little bit, time consuming, but I'll write the main elements of this. I guess this will be our lecture number 11 or something. Could it be 11 maybe? Let me just check. Yeah, that would be lecture 11 today. So today we're going to basically go over that, last example, which I didn't get to finish. And then I will try to transition to this more powerful architecture that I, have mentioned earlier, where we would have lots more instructions to interact with and to understand how. In fact, most of these things that we're going to see in this new architecture, you can find them in most of the contemporary, whether it's CISC or RISC architecture. Most of them are they have these so-called SIMD extensions, single instruction, multiple data extensions. And this architecture that I'm going to explain to you, describe to you, incorporates all those kinds of things into its own architecture, so that you can actually simulate these very advanced architectures, including ARM, Spark, MIPS, you name them. I mean, like any one of those machines is simulatable, if there's such a word, on this new architecture that I'm going to, describe for you. It's actually, in some respect, more powerful because you can also do graphics on this. What you can do in, like, for example, Apple's new chip M1. Actually, that doesn't have, by one account, that doesn't have SIMD extensions. But Apple's other ARM chips, like version 8 ARM chip, and other ones have SIMD extensions. And so will this one that I'm going to explain to you. So let's go back and then finish this first, and then I'll tell you about this other thing, which is like the sorting, sorting on VESP. So lecture 11 and sorting a list of elements on VESP 2.0. So our algorithm was like this, I guess, for I maybe 1 up to, let me just write this a little more briefly, to maybe n minus 1, and then for j I plus 1 to n, compare, let's just call this maybe m I and mj. Okay. And swap if mi is smaller. So if you think about this, starting at, for example, I equals 1, you're looking at the first element, m1, and then you go to the second for loop, and you're checking to see that if m1 is actually less than m2, in which case you just bring it to the left-hand side. And then, so basically you're trying to push it to the left. So that's the first, position. And you do this for all the elements from 2 all the way on to the last place. I guess this will, if you just think about it like this, let's just take a look at, maybe an array sort of situation. So let's say we have some elements here, maybe 3, 2, 4, maybe 5 and 6. So you start with, this element, let's say, and element 3, and you compare this. This is like, 1 position, like I is equal to 1. And you check that 1 element, and you say, okay, 3 versus 2. You check to see if, which one is smaller. Then you say, well, 2 is smaller, so put it here. Okay. And then you check that same element, which is now 2 against 4. Let me actually put a 1 in here so that you see what's happening. Okay, so in the next phase, so this actually becomes 3, 4, 1, 6. Again, you have 1, I is equal to 1, but now you move it to j equals, I guess, 3. And that you check 2 against 4. So, I is still equal, this is, let me just write these other things. This is, let's just be careful here. So here I was equal to 1, and then j was equal to 2. So you compare the 2, you move the 2 to the left, and now I is equal to 1, but j is equal to 3. And then in this case, you don't really touch anything. And then I is equal to 1, j is equal to 4. This time you move 1 over here, and then 3, 4, 2, 6. And then you finally say I equals, 1, and j is equal to 5. And then you say, well, 1 and 6, so it stays the same. So in other words, at the end of this process, the minimum element has just moved into its right place, okay? This is the minimum element, the minimum of all the elements here. Moved to the leftmost position. And so that's going to be an ascending sort, basically. We're going to sort things from the smallest to the largest. I see what happens after this. Of course, we increase I by 1 in the next iteration. So we're going to be looking at the substring or the sublist. And we're going to do the same thing. We're going to compare 3 to 4, 3 to 2, 3 to 6. So in the next iteration, you can see that 2 is going to move into position 2. During the next iteration, 2 will move into the right, into its position. Correct position, let's say, call it. So that we will have this. Okay, we'll have this now. So we're going to have 1, 2, 4, 3, 6, and you have gotten these in place. You go to the next place, you're going to do the same algorithm on this, and so on. Okay, so 1, 2, and then you're going to have basically 4 and 3 will be, switched over. That's the next step. And then, of course, these are in the right place. So you're going to get ultimately, finally, 4 and 6 got compared. That's what you're going to get sorted into ascending order. So that's what the algorithm does. And all we have to do now is to figure out a way to actually implement this algorithm in VESP. Otherwise, it's like we just checked the algorithm. The algorithm seems to work at the high level language which we have expressed it in. And of course, as we translate this algorithm, we have to be careful not to make any mistake so that, the translation is faithful, meaning that, whatever this level does of the algorithm, this representation, the one below it also does the same. So let's just look at this, this code for a moment. We got this number n, which actually we assume to be, in our earlier algorithms, assumed to be some constant like maybe 10 numbers is what we actually assume our list to have. But we can make this an entry in a memory location where we can update it. We can actually change that number without having to change the logic of our program. So in other words, it's a good idea to make it a variable in order to be able to avoid, making extensive changes within the code itself, if in fact it doesn't work, and then I have to change a whole bunch of stuff that may involve this variable n. So one thing that we're going to do in this edition, I think that may be just a little deviation from what we've been doing before, is to sort of like symbolize this size of the matrix, okay, which we call M here. And the other thing, of course, is now we have two variables that are actually running I and J. So one of them has to be our so-called IX register, our good old IX register, which we have built into VESP 2.0, which is something that gets incremented by itself whenever we access a memory location. And then the other thing, of course, is the other variable, which is J, which we have to think of as, another index pointer, but we don't have one. So we have to have one in place, meaning that maybe one of those locations, maybe the one right after location 2 in our so-called architecture, VESP 2.0 architecture, we allocate that second location, third location, let's say, I guess, 0, 1, 2, and then the one after that as our J. So let me just create the memory map, and then we figure out what to do in the actual specific steps of the algorithm. As I said, I may not end up writing the entire program, but I'll write most of it, and so you can maybe complete it on your own. And I'd like to move on to the next subject matter, because I think we've been that one class we did not have may impact what we're able to cover. Okay, so now to implement the pseudocode for sorting in VESP 2.0, we first map the problem to the memory of VESP. Okay. So let's go ahead and do that. I'm going to go ahead and do this right here. I think it looks like there's enough space. I don't know why this computer is just heating up here, not heating up, but doing something which I don't like.
Professor, can I see what you wrote?
Oh yeah, sure.
Thank you.
Something is kicking in here, which is this CF helper. I think I just didn't want to quit this Adobe. Force quit. This is always kicking in here. I think that's why. I'm just kidding. It's okay. I'll just quit this Adobe business. Hopefully that will be the one that will just. Yeah. So. Okay. So let's just create this map. Okay. And so this is our location 0, which is always A, our accumulator. And then here's location B, which is our 1, which is our co-accumulator. And then we got this IX register here, which we're going to use for our I. And then we have the next location, which I'd like to use as my J. Okay. Sorry about this. And then the next location, maybe I can, use that next location as the sort of like upper boundary of my array. Okay. So maybe this could represent, the upper boundary of our array. Okay. So we, that would be like not n exactly, because n is like, when I write it in a high level language, I say 1 up to n, but there must be some translation. This is what actually assemblers, are known to do. You have to get this n, which is basically some, bound on the number of times that we want to do this computation, like n is equal to 10. That means you're going to do this for loop 10 times or something. We are now specifying in this location the upper boundary of our array, because we're going to make comparisons in order to stop, our loops that will be like checking to see if our index register I or J has reached, its maximum. Now, in the case of J, we got to go all the way up to n. If you just look at the code that I've written up here, you can see that we go up to n for J, but for I, we go to n minus 1. So, if I write n to be, for example, the last place in my array, like the address of the last place, then J will run all the way up to that, but I itself has to run only up to n minus 1. Okay, so that's something that we have to keep in mind. I'm just going to stay, faithful to this this algorithm. Okay. All right. So let's see what we do. Okay. And then of course we have to put the array someplace. I want to move this array, a little farther away from the code that we're going to write. We're still going to start the code, or I guess alternative would be we could still put the array in location, for example, A, but maybe not just do that, because I think that also confuses that A with this accumulator array. So let me move the array somewhere else this time. Okay. So let's say that I'm going to place my array down here. Okay. Whereas this is like location maybe, 0x200. So I have a lot of space to write my code. If I assume that, my code is, this is This is where the array is. Okay, and it ends at the place which I'm going to specify by that number upper bound. Okay. Now, of course, I didn't show you here the, let me just do that also. Just maybe move this a little bit down. Okay. And maybe I can say that this is my, program. So this starts at 0x020. I just have to wait for this call to go away. Yeah, when I get a call from an unknown number, I normally don't answer or don't even hang it up. Okay. Okay. Okay, see if I have to stop that too. All right, stop. So that's how the layout is now. This is our layout basically. Okay, this is the layout of our solution. So so what we need to do is now write down the steps. Okay, so we can say, as the first step, initialize the array. So we're talking about a bunch of load instructions, and we said that this is going to start at location 0 to 100. Our array begins there. So you can write something like 0x020, and then the first instruction will be basically 200. That's where the first location of the array is, and you can put some number in here, right? I mean, I'm just going to leave these things, like whatever numbers we want to put in. We're going to sort these numbers. We can maybe like do this example, which I did here, handed, right? Like whatever it was that we started out with, 3241, for example. I could put those in there just as an example. Okay. So I'm going to put here a 3. Okay. And a 1, or a 2 actually it was.
Yeah, it was a 2.
It was a 2, yeah. Thank you. And I put that in. And then 0x0, 24, 2202. And it's a 3 in that location.
That's a 4.
Was it 4? Okay.
Yeah.
Thank you. And then in the next location, into the next location, I'm going to put in 1. And then the 6 comes last. So that's how the array is initialized, basically. Okay, so this is like, initialization process is completed. And you can see that we have put in, like ultimately 3, 2, 2, 4, 1, and 6. So altogether we have 5 numbers. Okay, so our n at this point in time is equal to like 5. Okay, and then we can initialize, the other places. So We can say initialize.
Professor, I'm sorry to interrupt, but
Yeah.
memory location 25 shouldn't it be 0004?
Yes, yes. These are all, yeah, that's right. Thank you for that. Yeah, thank you. You're right. No problem. So now initialize INJ. Initialize I actually, because J is going to be updated with I. Okay. So we're going to basically load into I the starting place of our array, which is location 200. So we're going to move into that or load into that location. So hold on. So this would be like 0x02a. And now we're going to put into location 2 our initial address, which is going to be basically 0200. Okay, so this is initial. This does the initialization. Now, as I said, the only other thing that we really have to initialize is at this point in time is the upper bound, because J is, if you look at the loop, J is something that actually dynamically changes within the code itself. You see how that J changes? This is I. So it's not 1 up to n. So we're going to alter that as we go forward. But the value that I mentioned, which is basically that, n, which is really not n, but the upper bound, as I said over here in the map, upper bound of our array, I have to put something into that place. Okay. So that happens to be location 4. And I'm going to initialize that location to n. The upper bound, a boundary of the array. So what that means is I'm going to put into this place 02c some initial value by saying 2004, and that would be equal to the last location where we put our number, which would be, I guess, 204. Okay. Do you see that, everybody? We start at 200, so we go up to 204 because we got only 5 numbers. Okay. So I'm going to basically do this. So now I've initialized everything that I want to initialize. I want to go out and do the actual loops. And in order to do that, I have to basically think back to the loops that I've written. This is a nested loop sort of situation. I'm sure that you've taken some C classes, some Java classes, some classes where you learn how to write nested loops. And that's what that was. Now we're going to do that within VESP 2.0. Okay. Yeah, this is just too big to hold, and also to, kind of like obscure my view. But unfortunately, the class is long, so I I end up having a big cup.
Enjoy your coffee, Professor.
This is tea,
Or tea, yeah.
and this is black tea.
I like black tea.
Yeah, I like it too. It's just very nice. With the chewing gum, it goes really well. Holds my hunger. Anyway, so let's get back to this. So now we can start our loop. Okay. So the way that we've been doing this, and I think it's maybe a good practice, is to check to see if we exceeded our boundary. In other words, that can happen one of two ways. In one of them, we'll actually go back to the beginning, but the other one is going to get us out of here. And what exactly is that? we get out of this place when this outer for loop expires. And you can see that, we set it to the first location, which is 204, that is, where our first number, and I'm sorry, 200, right? That's what we initialized it to. Let me just double check. I don't want to make a mistake there. That's it. That's right. That's what I was referring to here. So now we want to see if that's going to get up to 003, right? Because if it does get down to, get up to 2003, which will be like that place, that's when our outer loop expires, because we go up to n-1, not to n. So what we need to do is now to check to see if this I, which is initialized to 0200, has become 0203, in which case we're actually, or exceeded that, maybe is what I should say. We have to do that also, but we should not do 0204, because that would be like too many steps. We have to bail out, as you can see here, when the address gets to be n. We go up to n-1. So if this becomes n, that means we're done. We passed the loop. The last iteration of the loop is over. So I'm going to check now. I'm going to check if this number in I has become 204. Okay. So that's the check step. So how do I do it? Of course, I have to load what is in the IX register into A, and then I have to load what I consider to be the endpoint, the upper bound of our array, and then just perform a subtraction between the two. Okay, let me go ahead and do that. So 0x 0 to 6, copy. It's a copy now, not a load. 0 0 0 0x 0 to 7 0 0 0 2. Okay, copy IX into A.
Professor,
Yep.
why all of a sudden from 0x02C you jumped to 0x025? Doesn't D come after that?
What is that? What did I do?
So
That's
that's
a D. Yeah. I
yeah.
don't know why I did that. Yeah, I have no idea why I wrote that.
So now
Right?
instead of 26 you have 22E.
I know. I'm going to fix those two.
Okay.
I appreciate that, Yekta. Thank you. It's a very, I don't know what made me write that. Great. F, yeah. Yeah, please stop me when you see an obvious mistake. So copy I into A, okay? And then copy, now we go to 30. Copy what is in 4 into B. There we go. And yep. And now we want to perform a subtraction, okay? Copy the upper boundary. This is a little bit, we could have given a name maybe. Okay, and perform a subtraction, meaning complement A. Add first of all. No, not add, I'm sorry. Complement. What am I doing here? Okay. And then add the two together. And then you want to increment the A, and we have an increment instruction. I guess that was an 800, right? That was our increment. instruction. And so now we have tested to see, or we made the subtraction. So in other words, these things basically subtract. Okay. Perform.
Professor,
Yeah.
I think the you missed the spot. So 004, yeah.
Yep. Yeah. Thank you. Thank you. Okay. And so here's perform a subtraction, which is to say, we're subtracting basically, we're doing this, I guess we're doing the other way around, but that's okay. Okay, so, upper boundary minus I. If this is 0, that means, we've gone too far. Okay. We should not do any more comparison, which means now we have to quit out of here. So we go to halt. Sorry. What was our halt code? It was 5.
Jump to
of 0.
0. Yep.
5xx. xxx is where the halt instruction is going to be. Okay, so now we are into the interior loop. Okay. And now we want to check to see if we are actually at the end of our interior loop. We're just using the same principle. The exterior loop has been tested. Now we're going to go test the exterior loop. So what we want to do in this case is actually load J, the value of I. Okay. So the first thing to do is then to copy, actually before we copy J, I into J, what we want to do, let me see exactly how we do it here. Yeah, so we want to basically get the value of I and increment it by 1. As you can see, J is going to have to be set to that, just looking at here. Okay. And then check to see if that number is equal to, it has passed n, which will be actually like 1 larger than the one that we had before. So the step that we have to do now is to increment I and then test to see if that has exceeded the value of n, which will be the upper bound on n. Okay, so let's go ahead and do that. Okay. So at this point in time, we want to bring, since we messed up A here, or I, we played with it, let's just go ahead and copy it again, get a fresh copy. Okay, 3. Get a, okay, a bit harder sometimes. So we want to copy into A what is in I. Okay. And we want to increment it. Okay, so we say 0x038, and that's 8000. So now we computed I plus 1. And since we want to do this check on J, not so much on I, we want to move this into J, and then we want to bring it back into A because we're going to set up a loop loop to get back into this place. Okay, so this may look a little bit counterintuitive at first, but the idea is to sort of like put the value of I plus 1 into J and then run a loop test on J. Okay, so now that we incremented this, we can actually copy it into, so we just have to save it in a way. Next time we get through here is be another value of I plus 1 that will be pushed into J. So our loop will actually be somewhat contained in the statements that will follow. So let me just go ahead and do this. I'm going to save now whatever I got in the accumulator into, so this is increment, copy and increment. I save it I plus 1 to J. Does that make sense, Yekta? Okay.
Professor?
Yeah.
So I think it makes sense, but why, and I think you kind of start touching on this a little bit, but why not just copy I into J originally and increment J?
You could. I guess you could do that. But what I'm going to do, I'm going to come back. I'm going to do another, a couple of, I'm going to do another instruction, and you'll probably understand why I'm doing this. Let me do this
Got it.
next instruction, and then you tell me, maybe you can go your direction. So here's what I'd like to do. Okay. 0, 3b. And I want to get that thing back into the accumulator. Okay. Like so. This may look redundant, but it actually makes our life easier. Okay. Because I'm going to return to this place in my next loop. In other words, this save value of J, which has just been created by incrementing I plus 1 and storing it in there, is where I want to, keep coming back to. But in the meantime, I would be updating J as I finish my interior loop, so that the effect of this saving will not be, felt this way. It will just be affected right here. Does that make sense, Gabe?
Yes, it does.
I'm going to come back to this loop, and what I want to do is to increment J and then test it. And the way that I will be able to test it is by moving J back into A. This is where the test is going to happen. So I'm really anticipating what I'm going to do later in order to write this part of the code. It's a little tricky, but I don't think it's that complicated. Okay. This is where I'm going to go back to. Okay. So this is like having this interior loop separated from the operation of, incrementing I by 1 and then copying it into J. If I overlap them, I don't know what may happen. You can think through that and maybe save an instruction or two, but this is sort of a clear cut. I know that now when I'm getting back to this, I'm going to be in the interior loop. Okay. So now that I've done that, I'm going to test the same way that I've tested the I to see if this has become N. If it has, that means I've gone past my step, interior loop wise. Okay. So I'm going to now do so now that J is in, J is in A, I want to bring into B the number that happens to be in N, that is in the upper boundary business. So I'm going to copy that also, but I'm going to push that into 1. And that was in location, I guess, 4. Right? It was 4. Okay. Copy N. Now, if it's equal to N, then I should be doing this, right? Because J runs up to N. So that means whatever I put into this place has to be incremented when I'm doing my test. So let's say that I complement. Okay, now I'm just going to do a subtraction. That means for that I have to do a complement. Okay. And I want to do an add. Okay. And I have to add 1 to this, which is to increment. So if I had just done this, I would have been actually comparing n to a, not n, but the boundary address. Whereas I should have done this to n plus 1. So what do? I add 1 more, increment this 1 more time. Okay. So this is going to check if in fact I hit n plus 1. Okay. So all of this check if J has gone past the, what do you call it, upper boundary something? Yeah. Upper boundary of the array. So if that's the case, I'm going to get a 0. Okay. And that means at that point in time, I have to say that I'm done doing this. And this is where I have to go back. Okay. This is what I was trying to say. Now I have to jump with a 5, but the address that I want to jump back is here.
The outer loop.
Actually, not the outer loop, the inner loop. That will be, let's see. So actually outer loop, I'm sorry. I'm done with it, right? I'm getting out of it. You're right. So the outer loop is where I have to get back to. You're absolutely correct. Otherwise, I'll make the exchange and go back to that. So outer loop begins where? Right here. Who said outer loop, by the way?
Oh, me.
It was you, Jasser? Yeah, I think it's the outer loop because we're actually out of doing this, basically what we did by doing this comparison. Yeah, you're right. You're right.
I think we start at a upper loop of 2C.
So what, yeah, let me just say this, Yekta. So we basically are saying that we've done this for one I. I have to go back to check to see if I has actually gone past its own boundary. So we're going to go back to the loop where I has been updated so that we can do this inner loop one more time. Okay. Or not. So that we have to go back to that. So I guess that happens right here. Let's just make sure that we get that initialize I. So this is it. This is it. This is where we go back. Okay. However, before we go back in there, did we ever increment I? Let's just check that. All right. Nowhere did we increment I, did we? We never did. We did not have a move instruction like MXF that would have incremented I by 1. We haven't done that. So if we just go back to the beginning, the value of I has to be incremented by 1. So before actually we go to let me just do it this, yeah. So I think I want to increment. Okay, so let me call it Y, Y, Y. And in that place, Y, 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 I'm just going to increment, I by 1 and then go back to the beginning. Okay. Let me just write these addresses. So this is where the halt address. And this is increment I and return to the outer loop address. Okay. All right. So if that's not the case, this is this is where the juice of the algorithm is. Now we have to do the comparison. Okay. So now this is like when we get down to this next place, 0x04344. This is where we're going to make a comparison. There are two things that we have to bring down into the A and B registers. And we have to then perform a subtraction between the two and then figure out if the result is greater than 0, for example. If it's greater than 0, we don't make any exchange. If otherwise, if it's less than or equal to, we actually make a change, that is swap the two as we map them back to their places. Okay. So we let me just write this, and then I'll just copy that address again. So here we must compare MI and MJ and swap them if MI is less than MJ, right? Because we want to put, actually, no, I'm sorry, just the other way around. MJ is less than MI. We want to put what is in MJ into MI because I is the place where we're fixing these smallest numbers every time we iterate. So let's just go ahead and do that, see how we can actually manage to do this, right? So we haven't incremented I. I is the value that, we only increment I if we go exit by way of 5y business. So when we get down to here, I is the value that we actually began with. Okay, so what we want to do is at this location, let me just copy this down. The first thing is that we want to bring, and that's not that bad. It's actually E000. Whatever is an I now become I plus 1. Okay, so this brings MI to A. Okay. And now how do we bring the next one in? A little tricky. Any ideas?
E00, are we trying to put it in B or something?
We want to bring something into B.
So E001?
Yeah, but that's not coming from I index. It's coming from the J index.
Would we do an auxiliary move?
That's an idea, right? We can have a couple of moves. That's one way to do it. So in other words, we rely on our earlier technique, which is to say we put a move that will update the address from where we actually want to grab this. And that, of course, has to be that we want to move what's in a location 4, was a location 3 rather, into that place. So let's actually give that a try, see if it works. So I think, was that you, Jay, sir? Who was that? Gabriel? Gabe?
Yeah, it was Gabe. Yeah.
Yeah, let's go ahead and do that. Okay. Okay, so let's just try that. 3. Now let's write the addresses here. Okay, and then let's just write one more. So our, source will be 0, 0, 0, 3. That's where our j is. And the one that we want to alter is 0, 4, 8. Okay, and this is a move instruction that's going to move the thing into 1. So it doesn't matter, what this is. We don't care about it. We're just going to destroy that. So that should take care of it right there. Okay. And so this will actually copy basically, okay, let me just say this, these 4 instructions. We could have also used the IX register, but I don't want to mess with it too much. I could have moved what is in J into I and then use MXF again. Like I think Yekta was suggesting, except that we would have I in there as opposed to J. And we had to move the J first into I and then could have done that. But that would have, then mixed these I's and J's together, which I think is maybe not a good idea at this point in time. So now these instructions collectively, it's an auxiliary move business. This will basically auxiliary move. Okay, now we have MJ moves into B.
Professor, don't we increment I when we're using the MXT? So I is
MXF, you mean?
Oh, it's not the MXT. I'm sorry. I think that confused it. Okay.
Yeah. So your question is like, do we increment? Yes, we increment it, but we're not using I. We're going to actually deal with that at the end of this.
No, I was saying because I remember like the MXT and the MXF
They
instructions
increment by
up.
1. IX goes up by 1. Yeah.
Yeah.
That is true. Yeah, that we, so we have to keep that in mind. We now know that I has been increased by 1. That is so true.
And
Okay.
I increases by 1 with both MXF and MXT.
Yes, both of them. They work the same way. Yeah, we don't decrement I in the MXT. There are, in the next architecture that I'm going to tell you, there are lots of different ways of doing that. Like, when you write in Java, you plus in front of J, like first increment and then, use it, or decrement and use it. Those options are actually available in the other architecture. Okay, so let's just not, lose our train of thought here for too much. So now we have the 2 numbers in there. We want to basically complement and add 1 to look at the difference. Okay. So 0x049 will be to complement A, and then 0x04A will be to, I hope I'm not missing any addresses here because that will mess things up. Okay, just please watch my addresses, okay, in case I made a mistake. Like I make a mistake, let me know. Okay, so now we want to increment, which will be 800. So this is like, now we have basically, we have MI minus MJ in A. So if it's positive, then we don't do a swap, as you can see, right? If it's less than, like maybe I can say equal to, because I want to be able to get out of here without having to, because I only have instructions that will compare and jump if something is equal to 0, and jump if something is greater than 0. And I set it up so that I'm going to jump if something is greater than 0, back to the loop. Okay, that's why I just set it up this way. I put the I into MI into A and then MJ into B. So my subtraction is basically MI minus MJ. And if this is positive, that means I don't want to move anything around. Okay, so now this tells me that at 0x04C, I push a jump instruction in here. But before I jump, actually, I need to increment J by 1. Correct? Because we're now doing the interior loop. So I have to first increment J. For that, I have to go ahead and do this now, because when I come through, yeah, okay, so let me go ahead and do that. Then how do I do the incrementing of J? I copy it from location 0003 into location 000, and then I increment it by 1.
You just
And then
missed
I
one,
push.
Professor.
I did, yeah. This is what I knew that I was going to do this. Thank you. That was not deliberate, yet. I was not trying to test you. Just like, my mind works in so many different, cylinders here.
Okay.
Thank you. Okay. All right. 04F. So we have to push it back to where it came from, which will be this. So this is like increment J. Okay.
Professor,
Yeah.
won't that overwrite the contents at A?
Yes, but I think at this point in time, we know. Oh, wait a minute. I thought they were just jumping. Oh, yeah. No, I thought, okay. You're right. I haven't tested this, right? So the best way to do this would be like this. Okay. So I want to do this increment regardless, right? Whether I actually jump back. Okay. Let me just, do this. I'll just take this out of here. Actually, it will not work because of the end. Let me just do this. Okay. So let's just get out of here. 0, you're right. You're right about that. 0x, 04c. So I'm going to use 6, I think, is my jump if positive, and I'm going to call this maybe z, okay? Which will be like, below this next set of steps. And I have to watch my time. Actually, I thought that I will only do, I will just do part of this, but I'm going to end up writing this code for everybody. Let me just, because my machine is also going to lose power. There you go. So let's just go ahead and do this. And okay, so this is like, jump to increment J and return to the inner loop. Without doing anything, basically, without making any swap. But otherwise, we make a swap, and the swap will be like this. Okay, so what are we going to swap? We're going to swap now MI with MJ. So how do we do that swap? Okay, so I can bring MI into, let's say, location B. Okay, let's see if there's an easy way to do the swap. I have these indices, which I haven't actually touched yet. Let's say that I want to bring MI into B, okay? And then I can copy it from B into MJ, but before I do this, I also bring MJ into maybe A. So let's go ahead and do those copying things. Okay, so the first one is, again, easy. And I'm going to use the index register. But at this point in time, the index register has been incremented by 1 because I actually did use so-called this E instruction. So I have to actually decrement the index register. And for that, I have to go and copy it into A and then store it back into location 2. Okay. So let me go ahead and do this. You guys are following me still? I'm just thinking a lot here because, I haven't written the code before. So here's what I'm going to do. I'm going to copy into A what is in index register 2, and I will decrement it by 1. Just write this properly here. And the decrement is what? 900? That must be decrement. And then push it back into the index register. Okay. Now I have the right value of I, and I want to move from I want to move MI into I guess some location. Maybe I should not use A and B because I will still have to do some. Let's see, the value of J is has not been altered, right? So maybe I don't have to do anything about that. I could just copy directly that way. Okay. So let me just, move what is in MJ to a temp location, okay? So 0x0, but the problem is I don't know where J is pointing to, okay? So I have to do something about this. Now, okay, so here's what I'm going to do. I have to explain these steps. I want to move so let's just go ahead and 10 places here. I don't have to do anything about it. It's just that I want to write this. There'll be some temp spaces here. I'll write them later, okay? But I'm going to specifically use locations 5 and 6. I only need one, but right now my mind is a little bit cloudy on that. Let me just go ahead and do this. So I want to save what is now in MI to a temporary location. Okay. And so I'm going to do that by doing this. It's E, and I'm going to say 005. Okay. Temp for MI. So I've just done that. Of course, again, I has become I plus 1. Just keep that in mind. 0x053. Now that I've saved it, I want to now do the same thing to, actually at this point in time, I can do a move to directly take what is in, let's do another auxiliary here, okay? So let's just write the 0x054, 0x055, 0x056. Okay, there are 4 of them. So I'm going to say 3056. And I want to move what is in 0003, okay, into that location. And this is the real move. And for this one, I want to move this into the location where J points to. Okay. Now, so how do I do that? I simply, and that's in, I just copy that there, but this is going to go where I is going to, let's see, I want to move this into 0. Let's see if this actually works. Maybe I need a decrement in here. Yeah, I think before this, I need a decrement because that thing just incremented again. All right, so we need one more instruction before this. I need to decrement that I one more time. Okay. So let me just do this. I'll just do the following. Okay. And in here, I'm going to insert a decrement, which is 900. Oh, no, I can't quite do it that simply because I have to move that I back into A again. Sorry about this. So let me just do the decrement. Okay, this decrement is just adding a lot of work here. So here's what I want to do. 0x 053 3000 0x 054 0002 0x 055 9000 x 056. Copy it back. Okay, there we go. Okay, now I have the right value in IX. And I can do this, auxiliary move. And the way we will do it is we have 4 move instructions in here. Okay. So we want to move MJ into MI. And the way we do it is 3, 0, 5, B. And yet write 0, 0, 0, 3. And now we can use 3. This is the actual move. And then we would like to move. This is question mark. This is 0, 0, 2. Does that make sense, everybody? A little bit, overloaded at this point in time, but this actually completes these steps here. These move J into MI. And you know that we saved MI to temp. So we just want to take it from the temp location, location 5, and then push him to MJ. Okay. So now the next thing that we have to do, and I'm really out of time. I didn't realize. I knew this was going to take time. Okay, let's just go ahead and write a bunch of things here. Maybe this is where I stop. Okay. All right, Gabe, everything works out for you in your mind?
Looks good to me.
It looks good to you, okay. So now what is left to do is to copy what is in MJ, what is in temp rather, temp, which is location 5. We want to move that into where I is. All right, now what we did, we decremented J by I by 1 here, as you can see. and pushed it back into. So the value of I is actually correct at this point in time. We haven't messed with that with another move instruction. So what we can technically do is move let's see what I need to do here, right? So my I is where my, is pointing to the place where I have to make this replacement. Actually, no, my, the place that I want to move things into is actually in J, not in I, right? So I want to move, I want to copy what is in J into I, and then copy this number in there. So I think this is what we need to do. 3, 0, 0, 2, 0, 0, 0, 3. Copy J into I. Okay.
Professor?
Yeah.
Isn't that what we're doing right above with the auxiliary move?
No, I'm just moving now the index, addresses, not the numbers, not the array.
Oh, I understand.
Yeah, I'm just going to use that J as an index because I want to replace J. I was moving MJ into MI. Now I want to move MI into MJ, and I save this MI, as you notice, in location 5 over here. I want to grab it from there and then copy it to an address. Okay, but I think this time it has to be an F as opposed to E. So F, right? This time my address is like, yeah, I'm actually moving things into where the index pointer shows. In other words, the index pointer shows me the destination of the place, not the source. Do you notice the difference? I move J into I, and I is now like MXT instruction for me. I'm going to move to a location, something that sits in location 5. So move temp, which is actually I into MJ. Okay. And that's it. That's where I think, we're done with this. And by the way, remember that place where we would jump to? Here I said jump somewhere. Jump to increment J and return. The triple Z would be this address. This is the triple Z address. Okay. And what do we do in this case? We increment J by 1. So let's go ahead and do that real quick. Okay, how do I increment J? I simply move it from where it is into the accumulator. Okay, so this is really 0x 05f, 0x 0, 60, and then increment, which is 8000. Okay, incrementation is done. 0x061, and then jump back. But before we do this, because we have to push it back, 0x062, and that will be push it back, meaning like this, and then 0000, 0x063, okay, and then jump back as a forced jump. And where do we jump back? We jump back to this place where I said I'd like to jump back here because I'm just copying what I stored in J. Remember that place, everybody? Gabe?
I don't remember that exact
Okay.
place.
Let's just look at it. I think I marked it here. Remember, here I was actually copying, saving I plus 1 to j, j plus 1. See, here's what I was saying there. Save I plus 1 to j, and then bring it back into j. You see how that is? Into the accumulator for the test, right there. That's where I'm testing now, j. This is where the test is basically done. Remember, the subtraction happens here. This is the check. You see that check if j has gone past? So that's where I need to come back. 0x03b, which is 03b. So that's where I go back here. 03b. And the only other thing I think that's left is to halt. Let's see, did we leave any address, in unused? Let me see. So I said that, 05F is going to come up here, remember? Up here somewhere. Where did I say? Not that one. There was a Y. There it is. There it is. Okay, so this is going to be, there was a ZZZ, I'm sorry. Where's that thing? There it is. So that triple Z is going to be this address. 05F. Okay, first of all, let's just replace that. Where is that again? This is 05SF. Okay, now let's see. What else is there? Okay. So this thing is, of course, something which we have not done. Increment I and return to the outer loop. Okay. So we have to do that somewhere. Okay, I'll just write that down. And then there's also XXX, which is the halt instruction, right? There, somewhere in there. XXX. Now that will be the very last place. Let me see. I think I have to do this increment and then return to the outer loop business. Let's just go ahead and do that somewhere. So let's say that I increment I, then how do I do it? At this point in time, I copy, unless I has already been incremented in here. The only issue now in my mind is I didn't actually save the value of I. Do you see that, everybody? When I moved that J into I may have just destroyed it. Do you notice that? I should not have done that. I should have actually saved that I before I moved that J into I. So that is a bit of a problem here, because I was just going to write here increment for I and then go back, but I can't quite do this. All right, let me write a couple of things here. This is why I said I'm going to leave this, a little bit to your to you to finalize. Okay, it's just like 066. So one of them will be there could be several places here. One will definitely be halt. Okay, that would be, I think, the very first instruction. Let me just, just write something here. It may be just four steps, maybe more than enough, but I have to fix something else there. So here I have to just simply, put a 7000. And 069 would be this address. The only thing that I just noticed that I destroyed I in the process. Sorry. This XXX business here would be, right there, will be 069. Okay. And that Y is where the increment of I is going to happen. I just realized that I should have been saved. And unless we saved it somewhere, I never did. Yeah. So the only thing that needs to be resolved, okay, here we need to increment I and then go back to the main loop, to the outer loop. The only problem is, that we destroyed I when we moved J into it. So that's something that must be fixed, and we have to fix this. So we need to fix this. Okay, so I mean, that means before I actually do this step, these have to be adjusted a little bit. That means like we have to save it somewhere and then move that J in there if you want. The other option would be actually to use an auxiliary move in there somehow. But that needs to be fixed. Once you fix that, everything else is in place. So that's why I said I think I won't, give you the complete code, but something that's a close relative of it, if you like. But I would actually, when I find some time, I'm going to type this code myself into my own computer. I recommend that you do the same, and then see if in fact you get what is supposed to happen, just to get those things sorted. Okay, I think you have 99% of the code in front of you, and I think it's maybe something that you have to play with a little bit in order to tweak it a little bit to get it working. Is that okay, Gabe?
Yeah, sounds good.
Yeah, the main ideas are there. I think we just, because I had to rush towards the end, I just realized I was getting out of time here. But yeah, there, I think the J going into I just destroyed it there, right there. And we should not have destroyed I in there because we needed that I to get back to the main loop, outer loop, to complete the process. Okay, but that's an easy fix. Just simply save that I before you move it, move J into it, and then use that to restore that I before you get out of there to do the rest of the program that comes after this place here. Well, I thought that I was going to be able to get started with the new material, but I knew a little bit that when you do things in assembly, they may really take time and just kind of burn our entire class. But I think we may have even done overdone this, but I think you probably are very comfortable by now, playing with these machine codes. I don't think you will have any serious issues if you followed everything that I've done up until now. You just have to continue to use your mind and logic to see exactly what you should do when you try to hand assembly. This is what we're doing. We're hand assembling a C++ or some pseudocode into VES machine. That's all we're doing. All right. With all of that, I hope that you guys take care, and that there will be a Thursday class, and we got one more week to go before the break. And I did assign everybody a homework problem, and I think I've given you sufficient time to get it back. So it's I think 21st of March is when the homework is due. Hopefully that will be enough time for you to be able to maybe complete it. Okay.
Really quickly, I just wanted to clarify something.
Yes, Jillian.
For the both the MXF and MXT instructions, do they both have the internal incrementation of IX included in them?
Yes,
Okay.
Yes, they do. That's why we've been trying to be careful with them. And whenever we use one of those, the I goes up by 1, and you have to, if you need the original value of I, as we've done in this case several places, you have to decrement it.
Is there a reason why that's advantageous? Because a lot of what we've been doing today, clearly we don't like that, but is it that in more cases,
well,
you like that more than you don't?
Yeah, so I guess the one reason that they do this is if you have you have an array of elements, and you don't have to share that index pointer, maybe. In our case, we had this, we had to sort of save it and then restore it. And so it's the same index pointer that gets used for different purposes. In that case, it kind of loses its value. I tend to agree with you. But if you could set up several index pointers like this, in fact, you can see that in the next architecture, that's exactly what we have. then you can independently run these arrays and then have these incrementations happen by themselves. So that next time you go, like if a for loop where you just get mi equals maybe like mi minus 1, and then like you want to do this for the next I and next I, you don't have to increment this yourself. In other words, machine kind of like goes through a list of numbers or array of numbers and automatically increments or decrements. I guess this is like this. I mean, like maybe the easier answer would have been this: when you write Java or C programs, would you rather have like I++ in there, or you want to just like separately do this? I know that you write it into the main syntax, but that's something that like that's what you do, like I equals I plus I+1.
Mhm.
And so the translation of that is like increment I every time you go through the loop. It's just that we needed to get that same register IX for different purposes. Like the last one, which messed the things up here. Like I had to put the J in there so that I can actually, do the move, because otherwise we had to use auxiliary moves. And so I had to take advantage of that IX, but that at that point in time, I didn't realize I was going to increment I and go back to the main loop, and so I lost the I there just by moving J into I, because it's the same common, it's like the same thing that I'm sharing with a bunch of other things that I have to do. It's like A and B is when you have you have to save them. That's why we have these variables like sum, this, that, and then you just simply save things. You cannot afford to leave them in A or B. IX is the same way.
Okay.
Does that make sense?
Yeah,
Julian?
that makes a lot of sense. Thank
Yeah,
you.
we're down to 2 people here, by the way. I didn't everybody left. Okay. All right. So I'll see
Thank
you.
you.
Yeah, you're welcome. Bye-bye.